meters terminals and connect the other terminal to the ground through the framework of the machine. Now, instead of sparking, and connect the other terminal to the ground through the framework of the machine. Now, instead of sparking, the electricity can go through the meter to the ground. The moving spot of light tells us that an electric current is there. This current is a movement of electricity set free by rubbing materials together. We can also get electricity to move in other ways. Take these two metal wires, for example, that we're twisting together. They're each made of a different metal. We've connected the other end of each to the same meter. Watch the light spot on the scale as we heat up the join. This has nothing to do with sparks or rubbing. Electricity is in the wires. The heat is setting it free and causing it to move. There's electricity in the wire of this coil, and we can make it move simply by moving a magnet in and out of the coil. Perhaps the most well-known device we use to push electricity through materials like wires is the battery. Here, we're going to use the battery to push the electricity through the connecting wires. But can we use a battery to push electricity through other materials? What about a liquid? Does that contain electricity? Here, the liquid is a solution of copper sulphate. To connect wires to it, we're using a piece of copper pipe and a carbon rod. The meter tells us that electricity is on the move. So that means there must be electricity in the liquid, and the battery is causing the movement. If we leave the electricity moving through this liquid long enough, something very interesting happens. The carbon rod has become coated with a thin layer of copper. This copper has also moved through the liquid and has come from the copper connecting rod. This effect is sometimes used in industry to obtain really pure metals. Silver is one metal that can be purified electrically. The impure slabs of the metal are first enclosed in a cloth bag. The bag is very important. It's designed to hold back the impurities that will be left behind during the refining process. Once safely in their bags, the silver slabs are hung in a chemical bath. They're placed between plates of stainless steel so that they're just separated from each other. The refining process uses the fact that electricity is in the materials and can be made to move through them. We can see how it all works in a diagram. The stainless steel plates hang in a chemical called silver nitrate. Between these plates hang the silver slabs, or silver anodes as they're called. The anodes are connected to the positive side of the electrical circuit, the pushing side, while the stainless steel plates are connected to the negative side of the supply, the pulling side. As As the current flows, pure silver is gradually carried away from the impure anodes to the stainless steel plates. It builds up in the form of pure silver crystals. From time to time, the plates are lifted out of the bath to remove the silver that's collected. The crystals are almost completely pure, coloured only by the liquid that's draining away. Pure silver is an extremely good conductor of electricity. It's easy to push electricity through it, so it would be a very good metal to make into electrical cables. But the trouble is, silver is also very valuable. So instead, it's melted down and cast into ingots for use by bankers as a form of money. When it comes to moving electricity from place to place, we use a whole variety of materials, each chosen for their properties, especially their electrical properties. Let's take a look inside this underground cable. At the center is a material that's easy to push electricity through, a conductor. This one's made from a bundle of copper wires. A metal band holds the wires together, and that's surrounded by thick layers of oily paper, an insulator. It's a material which is very hard to push electricity through. Round this, there's another band of metal, then a layer of lead protecting the cable from mechanical damage. Another metal band prevents interference on radio and television, while an outer layer of pitch keeps the moisture out. Above ground, electricity is carried by aluminium conductors. To insulate these conductors from the pylons and the ground, we use these strange-looking pillar-like structures. In the laboratory, we can connect one of these structures into an electrical circuit. And we can apply a steadily increasing push to see if it's at all possible to get electricity to flow through it. This flashing arc tells us an electric current is flowing, but it's not flowing through the solid insulator. Instead, it's flowing through the surrounding air. So under certain conditions, air can conduct electricity. If the air should ever conduct around one of these insulators, the resulting flash could do a lot of damage to them. To reduce that risk, specially shaped pieces of metal are fixed at each end of the insulator. They're called arcing horns. In the laboratory, you can see what happens if the air conducts now. The arc forms between the metal horns, well away from the solid insulators. These insulators are made from a ceramic material. It's one that's almost impossible to push electricity through. Another material they're often made from is glass. Could glass ever become a conductor? This electric light bulb is part of an electrical circuit. We're about to complete that circuit with a piece of glass rod and try to push electricity through the completed circuit. This is not an experiment you should try yourselves, as the push needed comes from the mains. When we switch on, nothing happens. The glass is an insulator. But what if we heat the glass? Now it's almost red hot. And the lamp is beginning to glow. Heating the glass has made it possible to push electricity through it. If we allow the glass to cool down, it will eventually become an insulator again. Every electrical device, including this light bulb, is made of materials that are chosen for their properties, particularly their electrical properties. Inside the light bulb, for example, there's a coiled filament made from a material that will glow white hot when a current is pushed through it. The material is an electrical conductor. It glows because it resists the flow of electricity. All electrical conductors offer some resistance, some more than others. These two coils are also electrical conductors, but they're made from different materials. This one is copper. The other, a metal alloy called manganese. When we switch on, the same current will go through both coils. The copper coil remains cool. But the manganese gets hot. That's because the manganese resists the movement of electricity through it much more than the copper. Every time you use a toaster, you rely on a metal conductor getting hot because of the resistance it offers. Between these two terminals is a tiny piece of fused wire. We've connected it into a circuit so that a current can be made to flow through it. Like other conductors, it offers some resistance to the flow of electricity, which causes it to heat up. The greater the current, the hotter it gets, until eventually it can melt and break the circuit. This is how a fuse works. Now let's see a fuse in action. We've set up this power drill so that we can increase the load on the motor by tightening up a vise on a steel shaft being turned by the motor. When the motor stalls, the fuse blows, breaking the circuit. But what would have happened if the circuit did not contain a fuse? We'll put a thick piece of copper wire in its place. Again, we'll overload the motor. The copper wire appears to be unaffected. Instead, something inside the motor is heating up. It's extremely dangerous not to have a suitable fuse in the circuit. Of course, an electric motor depends on a flow of current for it to work. But just how does a flow of current produce movement? Let's find out. Here, we've suspended a metal rod between the two ends of a specially shaped magnet. We've made connections to the top and bottom of the rod so we can push an electric current through it using a car battery. When the current flows, the rod moves. Now, what if we change the shape of the rod and repeat the experiment? By making it crank-shaped, we've been able to make it turn, but only halfway round. What happens if we wait until the crank is halfway round, then push the electricity in the opposite direction by reversing the connections? We can make it turn right round. And there's a simple way of keeping it going. The battery has now been connected to the metal rod through a metal disc divided in two halves. As the rod rotates, it takes round with it a metal brush which makes contact with the disc, first one side, then the other, so the direction of the current in the rod keeps changing. A simple motor. In a real motor, things may not look quite so simple, but the idea is exactly the same. Instead of one single metal crank-shaped rod, the current is pushed round a number of coils. And instead of the split disc, the connections to the coils are made through a metal cylinder split up into sections. But not all electric motors turn. This is a flat aluminium plate. Somehow, an effect produced by an electric current is causing it to float in space. We can do the same thing with this aluminium ring. We can even make the ring jump in the air. It's an effect that seems to be produced by pushing a particular kind of current through coils of wire. By arranging a number of coils in a line, we can make a piece of aluminium float and travel over them. One way of explaining how this happens is to imagine that the flow of electricity through the coils is producing a wave-like effect, which will carry things along with it. This wave will carry a ball. It's an idea that has led to the linear motor, a device which could form the basis of a transport system in the future.